In this video, we begin exploring ideas from Chapter 3. Chapter 3 begins by looking at how we balance chemical equations, a few different types of chemical reactions, introduces the concept of Avogadro's number, calculations involving empirical formulas, and then a lot of different calculations involving stoichiometry. If we stack up the ideas within this chapter, many of these ideas involve bringing together chemistry ideas and mathematical calculations. Balancing chemical equations is the focus of this particular video. It's crucial within the chapter in several different ways. The skill of simply balancing them, most students do quite well at that particular objective. When it's paired with a word description, it becomes more challenging. And most challenging are particle representations. So within this video, we'll be trying to emphasize how do we understand chemical reactions at the particle level. The idea for balancing a chemical equation is simple. Atoms are not created or destroyed in a chemical reaction, so the total number that we have as the reactants must equal the total number of atoms that we have as the products. We can describe that in different ways. It could show what the particles are doing, molecules of H2 gas combining with a molecule of O2 gas to form H2O, or it could be given within the chemical formula. What information do you think the coefficient communicates? Within this balanced chemical equation, it says 2H2O. What does that 2 in front mean? And how about the subscript? H2O. What does the subscript communicate? Take a second, share your ideas. Here's the author's description of what they mean. Within the chemical formula, the numbers in front of a given formula, be it H2O2 or H2O, those are called the coefficients. They indicate the relative number of molecules of each kind involved in the reaction. If you don't see a coefficient, it's because it had a value of 1 and it was omitted. Subscripts? The subscripts, like in H2O, are telling us what that molecule is composed of. 2 atoms of hydrogen for every 1 atom of oxygen. That's what's in the H2O. So by combining both of those, you can see that the total number of atoms is obtained by multiplying each subscript in the chemical formula by the coefficient. If I were to add up here on the product side, 2H2O tells me 2 of the H2O molecules. Within each of those, I see 2 hydrogens, so that adds up to being 1, 2, 3, 4. 2 times 2 is 4. So this is that same reaction. The coefficient of 1 for oxygen, if it's not there, it's assumed to be 1. Here's another way that we might see this described. So initially, we have a sealed container before the reaction. I see 2 molecules of hydrogen gas and 1 molecule of oxygen gas. After the reaction in that same sealed container, I now see the products. So particle representations for chemical reactions many times are shown this way. A box that shows what was initially there, and then a box to show the final. Consider the description for this experiment. This is the initial, and then this is the final in the sealed box. What are your thoughts? Are these describing the same reaction? Do they have the same chemical equation? They look different. In what respect would you say they're different? How about this one here? Is this describing the same reaction? Does it have the same chemical equation as the other two? If not, what would be the correct chemical equation? See if you can make sense of these. This is bringing together particle representations and then chemical equations where you have to be careful with the coefficients and the subscripts. A resource to explore this is at the PhET website. One of their sims called Balancing Chemical Equations. It has both a game mode and an introduction mode. Here's the introduction. So there's 3 different reactions: making ammonia, separating water, and combust methane. Let's look at the separate water. the top, I'm going to have it designate how many of each atom are present. 1 water molecule, 2 water molecules. At the top, it's changing the relative number of atoms then that are in the container. To balance it, we need to make the total number before and after be the same. Currently not balanced. If we manipulate the coefficients, we can get the smiley face. This is the one that led to the smiley face. So notice that we're manipulating the coefficients, we're not manipulating the subscripts when we seek to balance the reaction. This is showing the decomposition of water into hydrogen, gas, and oxygen. This is just the reverse of the reaction that we used to first introduce the idea of hydrogen and oxygen combining to form H2O. Now, you might have heard that physical changes are reversible and chemical changes are not. Based on what we have on this screen, that seems perplexing, because we've just taken a chemical reaction and we've written it in the reverse. A common misconception is that you cannot reverse a chemical change. You can. Sometimes it's quite difficult, but there's no rule that says that it's impossible to reverse a chemical reaction. In fact, this is a very clear example. Both of those reactions are valid, both are applicable. A common misconception is that you cannot reverse a chemical change. It might be difficult to accomplish, but there are certainly examples. So this is the reaction to make ammonia. So what I'd like you to do is, first of all, balance this equation and then predict what are the particles going to look like at the what will the products look like at the particle level? Stop the video. See if you can make a sketch. What is it going to look like at the particle level in the products? Here's with the coefficients being manipulated to balance it. Smiley face, because you've got the same number of nitrogen atoms on both sides, same number of hydrogen atoms on both sides. What did you predict would be in the box for the products? This is what they're showing. Within this reaction, it's saying that nitrogen gas and hydrogen gas will combine to form molecules of ammonia. That's what NH3 is. The NH3 molecule is the product. If you're saying what's in the box, ignore the coefficient when you want to determine what the product looks like. Later on within this course, we're going to learn more how we would predict the shape of the molecule. But at this point, based on that balanced chemical equation, when I see that the product is NH3, I would say that the product will have 1 atom of nitrogen combined with 3 atoms of hydrogen. That's what's making the NH3 molecule. Here's one where we're being asked to analyze a reaction where a word description is given. Calcium metal reacts with oxygen gas to produce solid calcium oxide. What I'd like you to do for this one, write a balanced equation for this reaction, identify any species that are molecular compounds, and identify any ionic compounds. Pause the video, give that a try. At the particle level, they're showing what's going on. This is the calcium, the oxygen, and the product, the calcium oxide. This would be the balanced chemical equation. In order to balance that, you must know the formula for every reactant and product involved. If you said oxygen gas with just an oxygen atom, it would be incorrect. Calcium oxide, calcium's +2, oxygen's -2 within the compound. So you need to know those in order to correctly balance it. Molecular compounds, oxygen gas is oxygen molecules. I like this depiction where they're showing discrete molecules of O2. Ionic compound, calcium oxide, includes calcium cations, oxygen anions. That would be an ionic compound. Notice how there's this alternating pattern within a lattice. The calcium itself, that's what's called a metallic solid. So I'm bringing that up. Not every substance in the world is molecular or ionic. When you have metals all by themselves, you can have those atoms again and again and again. That would be called a metallic solid. We know that there's a lot of metals on the periodic table. Many elements in their elemental form are metals. So this description here of metallic solid, this would be calcium solid, sodium solid, silver, gold, iron. All of those metals that are shown here in red come in nature as metallic solids. Looking more closely here at the calcium oxide, this would be considered the formula unit. The formula unit is the empirical formula for any ionic compound. When we balance this, calcium oxide, CaO, is the formula that we would use in the equation. This is still an ionic compound. Even though we're putting this coefficient in front, that does not somehow turn calcium oxide into a molecule. Remember, we can ignore the coefficient when we're predicting what the compound is going to look like, either as a reactant or as a product. Here's two questions involving balancing chemical reactions. I'm including these in part because this is a very typical format for exam questions on this topic. What is the sum of the coefficients? So I would not expect on an exam to have different equations provided and it says which of these is correctly balanced. This is far more typical, where your objective is to take the chemical equation, balance it, and then tell something about the coefficients. Might be the total number, might be just the products, might be just the reactants. So you need to read the question carefully. This bottom one, this one's definitely driving home the fact that you need to be able to write the formulas given the word description. What is the sum of the coefficients in the balanced equation when aluminum hydroxide reacts with sulfuric acid to produce aluminum sulfate and water? Give both of these a try. The first one is a little bit more challenging in terms of being able to determine the correct coefficients, and the second one is challenging because you need to begin it by knowing the formulas for the different reactants and products. So within this video, we've been looking at ideas at the start of chapter 3, the information that are included in chemical equations. When we look at how the ideas fit together, that's a crucial one that we're going to need to have in order to accomplish many of the other tasks within the chapter.